Logics. In the previous class, I have discussed about the NAND gate, design and verification of NAND gate in a gate level model using Verilog, using this software called EDA Playground. It is not a software; it is a website. Okay. So today in this class, I am going to discuss about the same NAND gate. Okay. In the previous class, we have discussed about the gate level model, right? In which we have used the primitive that is NAND, and then given the instance name, followed by output, and then input. So today in this class I am going to discuss about data flow model. Okay, data flow model. We are going to discuss the code of data flow model of NAND gate. So from module to the semicolon to this point, everything will be same. Okay, everything will be same, and the end module is same. The logic which I have written in between the semicolon, this semicolon and the end module will be changed for the data flow model. Okay, we are going to write the code, design code in the design.sv. Okay, we are going to write the code over here. So I am going to remove the logic of gate level model and now writing the logic related to the data flow model. For that we need to use the assign keyboard. In data flow model we are going to use the assign keyboard. After assign you need to give the output variable, which is output port, that is y equal to, we know that for AND operation we are going to use the ampersand. We are going to do the perform the AND operation between both the input ports, and then finally we are going to perform NOR operation, that is this symbol. Okay, we are going to perform the NOR operation to the result. Okay, and then I'm putting the semicolon over here. This is how we are going to write the code in data flow model. Okay, now everything will be same. The TB you shouldn't need not to be change the TB. Okay, everything will be same. Okay, if you are going to change the name of the module over here, for example I am going to give the name of the module as NAND underscore gate underscore data flow, then what you need to change in the TB is you are going to instantiate, right? In that particular instantiation you need to give NAND gate underscore data flow. Okay, if you have modified the module name. Okay, if you haven't modified the module name, then you need not to modify anything in the TB. Everything will be same. Everything will be same. I am not going to modify anything. Okay, everything will be same. First what we have done is the inputs are becoming the input ports will become bridges in the TB, and the output will become wire in the TB, and then we are going to instantiate the design module in the TB to apply the inputs, and then we have a initial begin block to apply different input test cases. Total we are having two inputs. Those are two, we shouldn't tell them as inputs, we should call them as test cases. Total we have two test vectors or the test inputs. Those are A and B. Because of 2 we are going to have total 4 combinations, that is 2 power 2, 4 combinations from 0 0 to 0 1 1, that is 0 0 0 1 1 0 1 1, with the certain amount of delay specified over here. Okay, and after 0 nanoseconds of time we are going to apply A equal to 0 and B equal to 0. After 10 nanoseconds of time we are going to apply A equal to 0, B equal to 1. After 20 nanoseconds of time, from 10 nanoseconds of time, we are going to apply the A equal to 1 and B equal to 0. After 30 nanoseconds of time, from 30 nanoseconds of time, we are going to apply A is equal to 1 and B is equal to 1. After 30 nanoseconds of time, from 60 nanoseconds of time, we are going to stop the execution of the simulation. We are going to stop the simulation. Okay, this is the code works. This is the applying of the test cases to the DUT or the module, design module, which we have instantiated over here. This initial block, what does it do is the $monitor is used to print the output of our simulation in the log file over here, and the dollar dump file and dump wares are used to display the waveform to us. Okay, are used to display the waveform to us. This thing, whole thing, I have discussed in detail in the previous video, and in also the first video, that is design and verification of NAND gate using the gate level model. In that video I have discussed in very detail, so that I am not going to discuss this particular TB in detail in other videos. Why? Because in Verilog we are mostly focusing on the design code. Okay, Verilog we are going to focus mostly on the design code. We are not worried about the TB. Okay, in system Verilog we are going to concentrate more on TB, so that I am going to discuss about only design code. So this is the design code of our NAND gate, right? This is NAND gate, right? Sorry, NAND gate using Dataflow model. So this is how we are going to use. We are going to verify. So now after writing the design code and test bench, you need to select the tool. You need to go to the tools and simulator option, select the first option. Now after that, what you need to do is you just simply save the code and then run the code. The desired output of your simulation will be displayed over here in the log file. See, at 0 nanoseconds of point of time, we are going to apply test cases input as a equal to 0, b equal to 0, and at that point of time we are going to get the output as 1. Similarly, at t is equal to 10 nanoseconds of time, or after 10 nanoseconds of time from instant 0 nanoseconds of time, from instant 0 nanoseconds of time, after 10 nanoseconds of time, we are going to change our input test cases from a equal to 0 to a equal to 0 and b is equal to 0 to p is equal to 1. At that point of time, we are going to observe our output y is equal to 1. At 10 nanoseconds of time instant, after 30 nanoseconds of, after 20 nanoseconds of time, that is at 30 nanoseconds point of time, we are going to change our inputs as a is equal to 1 and b is equal to 0. So we have observed the output as y is equal to 1. Okay, at 30 nanoseconds of time, after another 30 nanoseconds of time, that is at 60 nanoseconds point of time, we are going to change our inputs from a is equal to 1 to a is equal to 1 and then b is equal to 0 to b is equal to 1. We are going to observe the output as y equal to 0. So this is the operation of the NAND gate, right? Why? Because we are going to see whenever both the inputs are applied as 1, we are going to get the output as 0. In all other cases, we are going to see the output as 1. Okay, this is the NAND operation, which is opposite to the AND operation, right? So you need to know the truth table. Okay, without knowing truth table, you can't able to write this Verilog codes and all this. Okay, you need to know truth table to verify the code, to verify the output, right? So I recommend you guys to first learn the digital electronics. If someone doesn't know about the digital electronics and directly starting with the Verilog, they will suffer a lot. Okay, I recommend you guys to have an good knowledge in the digital electronics first, then only you can come over here. Okay, and then learn Verilog and VHDL and system Verilog, all these hardware description and verification languages. Okay, without knowing digital electronics, you can't able to do anything. Okay, so now we have seen our output in log file, right? That is console. Now let us see the waveform. To see the waveform, what you need to do is you need to tick this mark, that is open EPWave after run, and rerun the code by saving it. Okay. After rerunning the code, a pop-up of waveform window will be opened automatically like this. See, in which we are going to have our input and output test cases as A and B and then Y. Okay, at 0 nanoseconds of time, that is after 0 nanoseconds time, both is same, right? After 0 nanoseconds of time and at 0 nanoseconds of time, almost same. Okay, at that point of time, we are applying our inputs as sorry, Just a second, something went wrong. Let me rerun the code. Okay, we are getting different output in the waveform. See, now we got the correct output. See, at 0 nanoseconds of point of time or after 0 nanoseconds of time, quite similar. Okay, after 0 nanoseconds point of time, why only after 0 nanoseconds of point of time means we have specified like that in our initial begin block in the test bench, right? After 0 nanoseconds of time we need to apply our input test cases as a equal to 0 and b equal to 0. For that, for those test cases we are going to get output as 1. Okay, we are going to get output as 1. This green color indicates output high, that is 1, and the blue color indicates output 0, that is low. Okay, and after 10 nanoseconds point of time, from 0 nanoseconds of time till 10 nanoseconds of time, that is after 10 nanoseconds of point of time, from 0 nanoseconds of time, our our input stays as a equal to 0 and b is equal to 0, so that our output stays as y is equal to 1 till 10 nanoseconds of point of time, from 0 nanoseconds of point of time, that is 10 nanoseconds. Now at 10 nanoseconds point of time we are going to change our inputs. Okay, that is after 10 nanoseconds point of time, from 0 nanoseconds point of time, which is actually the 10 nanoseconds point of time. At 10 nanoseconds point of time we are going to change our inputs as a is equal to 0 and b is equal to 1. Okay, a is getting stayed as 0 while b is getting changed from 0 to 1. Okay, at this point of time we are going to see the output. There is no change in the output, it is staying as 1 only. Okay, now from 10 nanoseconds point of time we have specified 20 nanoseconds delay in the code. From 10 nanoseconds of point of time, 20 nanoseconds point of 20 nanoseconds delay will be equal to 30 nanoseconds, not 20 nanoseconds. Okay, from 10 nanoseconds of point of time the inputs are staying up to 20 nanoseconds point of time, that is still up to 30 nanoseconds point of time. Till 30 nanoseconds point of time our input is not getting changed, so that our output is also not getting changed. At 30 nanoseconds point of time we are going to make our input test case a is equal to 1 and output test case b is equal to 0. Sorry, input test case b is equal to 0 and input test case a is equal to 1. For that corresponding inputs we are going to observe the output as 1. There is no any change in the output till now. For all the three test cases, those are 0 0 0 1 1 1 0. Okay, from this point of time, okay, again we are going to wait till 30 nanoseconds point of time, which is from 30 nanoseconds point of time we are going to wait 30 nanoseconds point of time, that is up to 60 nanoseconds point of time. At 60 nanoseconds point of time we are going to change our input again as a is equal to 1 and b is equal to 1. For this corresponding input we are going to see our output as y is equal to 0, which is the operation of, or the logical operation of the NAND gate, right? From 16 nanoseconds point of time till another 16 another 30 nanoseconds point of time we are going to wait. Okay, we are going to wait and the input stays at a is equal to 1 and b is equal to 1 and the output will be stays at y equal to 0 at 90 nanoseconds point of time, which is not displayed over here in the waveform. We are going to stop our simulation. Okay, this is how the code works. This is the explanation of the waveform. Okay, y y10 y20 y30 and then y30 means we have specified like that in our code, so that it is behaving accordingly to our code. Okay, in our test bench code, first initially we specified 0 nanoseconds point of time, and then we are going to wait till 10 nanoseconds point of time. After reaching 10 nanoseconds after completing 10 nanoseconds, it will go reach the 10 nanoseconds time instant. At 10 nanoseconds time instant, we are going to change our input test cases. Again, we are waiting 20 nanoseconds. 20 nanoseconds point of time. Why only 20? Means we have specified like that. That's your wish. The time delay which you are going to specify in the code is your wish. Okay, so that it is going to wait to another 20 nanoseconds point of time from 10 nanoseconds of time. Okay, from 10 nanoseconds point of time, another 20 nanoseconds will be equal to 30 nanoseconds, not equal to the 20 nanoseconds. Okay, we are going to confuse in this particular understanding of the waveform and the delay. Whenever there is a concept of delay, we might get confused. In the first starting video of the design and verification of NAND Gate, I got confused, so that I am going to stress this point very loudly. Okay, so remember this point. Okay, and at 30 nanoseconds point of time, we are going to change our input again from a equal to 1 to a equal to 0 to 1 and b is equal to 1 to 0. Okay, again we are going to wait another 30 nanoseconds point of time. Why only 30 nanoseconds point of time? Means we have specified like that in our code in the initial begin block, where we have specified the input test cases values. Okay, another 30 nanoseconds will be equal to the 60 nanoseconds. Okay, in at the 60 nanoseconds point of time, we are going to change our input again, so we are going to get corresponding output. So this is how we are going to get. So in code I am going to tell you. See, after 0 nanoseconds of time, we are going to apply this input. From 0 nanoseconds of time, after 0 nanoseconds of time, we have applied this input. Again, after 10 nanoseconds of time, from which nanoseconds of time we have waiting is from 0 nanoseconds of time, we are waiting till 10 nanoseconds of time, which is now at 10 nanoseconds point instant. At 10 nanoseconds point instant, we have changed our input. Again, we are going to wait another 20 nanoseconds point of time. Now we are at 10 nanoseconds point of time. From 10 nanoseconds of point of time, another 20 nanoseconds point of time will be equal to 30 another 20 nanoseconds delay will be leads to 30 nanoseconds point of time, not 20 nanoseconds point of time, right? Again, from 13 at 30 nanoseconds point of time, we are going to wait another 30 nanoseconds of time, which will be equal to the 60 nanoseconds of time, not 30 nanoseconds of time, right? So you just code by yourself, then you can able to understand what I am going to tell you. Okay, this is how we are going to see the output. Don't worry about the TV. Okay, in the system Verilog, we are more focusing on the TV only. In the Verilog, we are going to focus mostly on the design code. So I am going to discuss design code in deep, and TB I am going to use the same. Okay, I am not going to change any TB which is over there. Okay, so this is how we are going to write the code in the data flow model. In the data flow model, you can also use another thing as well. That is, yeah, we can use another thing as well. We can also use the ternary operator, which I have discussed in the previous behavioral model. In behavioral model, I have discussed behavioral model of NAND Gate. I have discussed about the ternary operator, right? Like that also you can able to write the code. Okay, there is no any mistake in it. Okay, in data flow also you can write like that. That is, I'm now what I'm going to do is, in the truth table of NAND gate, you can see this is the truth table of NAND gate, right? Which we have got in the output. Whenever both the inputs a is equal to 1 and b is equal to 1, we are going to get the output as 0, right? Using this condition, I am going to write the ternary operator, right? See, whenever a is equal to 1 and logical and, whenever you going to specify the two ands, it indicates the logical and operation. Okay, whenever you are going to specify a equal to 1, which means it is a conditional operator, conditional equality checking. Okay, whether a value is equal to 1 or not. if a value is equal to 1, then it is going to give the output as Boolean 1, that is logical 1. If a value is not equal to if a value is not equal to 1, then it is going to give the output as logical 0. Okay, and the in between we have a logical AND operation, right? Now I am going to check whether p value is equal to 1. If this happen, means if this condition is true, then we need to get output as what? Then we need to get output as 0, right? See, we got output as 0. We got output as 0. In all other conditions, we need to get output as 1. Okay, in all other conditions, we need to get output as 1, right? See, in all other condition, we are getting output as 1. See, here we got 1, here we got 1, here we got 1. Only in this case, that is a equal to 1 and b equal to 1, we are going to get y is equal to 0. That thing only I have specified over here. Why only the condition, that is y a is equal to 0 and b is equal to 1, means in this condition only we are going to have a different output compared to other test cases. Okay, if you would like to specify this condition, which is a is equal to 1 and then b is equal to 0, okay, like with corresponding output will be y is equal to 1, right? Not only for this particular test case we are getting y is equal to 1, there are some other test cases as well. So you need to specify three of them in the same condition, and you need to write y is equal to 1. Okay, but instead of writing three of the conditions in the same ternary operator, you just specify this condition, and then you are going to get output as y is equal to 0, right? So what I have done is, see, I will tell you clearly. See, we are going to have y is equal to a is equal to 1. So what happens, I'm going to tell you. Okay, and then logical AND operator, and then b is equal to 1. B is equal to 1, and we have the question mark. Okay, just catch my words. Okay, this is a colon, right? Sorry, this is colon. Let me again write it. See, this is the colon, and then I have mentioned the semicolon, right? See, as per, if you are going to watch my previous videos, then you know, right? That is, this is the condition. Okay, if this condition evaluates to true, that is, if you are going to get logical 1 over here, or if this condition is true, then the right hand side value, which is 1 in this case, will be stored in the LHS port or variable. Okay, if this condition is false, that is else to 0 or false, then the right hand side of colon, which is 0, will store in the variable y, right? So I think I have interchanged, right? I have interchanged. This will be the 0 and this will be the 1 in our case. In our case, it will be the 0 and it will be 1. Okay, it means whenever the condition is true, we need 0 to be stored in the y. when our condition is false, we need 1 to be stored in the y. Okay, so now how this condition is going to be checked? So in these particular braces we are going to have total 3 operators. Those are, one is equality checking operator, there are 2 equality checking operators, and then a logical and operator, right? So according to the precedence, okay, operator precedence, the logical and operator will have low precedence than compared to the double equal to or the equality operator. Okay, so that whenever you are going to give the test cases, that is, for example, we are going to have test cases of a b in the tb, right? We are going to have total 4 test cases. Those are 0 0 0 1 1 0 and then 1 1. Okay, whenever you are going to give these test cases of or the values of a comma b in the tb, these respective values will be replaced by the variable in the equation, right? So it means whenever I am going to take the condition as 0 0, now in place of a we are going to have 0, and in place of b we are going to have 0. Is 0 equal to 1? No, right? False. It will result to 0. In this whole position, we are going to get it is replaced with 0. Why? Because the condition is false. Why? Because 0 is not equal to 1, so that it is going to give 0. Similarly, in this condition as well, it is also false, so that we are going to replace it with 0. Now we have 0 logical and with 0, which is actually 0, right? 0 logical and with 0, which is actually 0. It means the condition got false. 0 means the condition is false. So if the condition is false, what it need to be stored means the value which is right hand side of the column is needed to be stored in the variable y. It means one will get stored. I shouldn't say stored here in this case. Why? Because it is a data flow model, right? One will be driven by y will be driven with value 1. Okay, y will be driven with value 1. It means we are going to get output as 1. Okay, similarly if you are going to apply 0 1, you are going to get 1. Why? Because this condition will be false and this condition will be true for this 0 1, and then 0 logical and with 1 means we are going to get the result as 0, which is false. So that again one is getting driven, one is getting driven in y. So similarly 1 0 1 0 also we are going to get output as 1. Coming to 1 1, here one is checking with the 1, and here as well we are going to check 1 with 1. So the both the conditions will be true, right? So that 1 logical and with 1 will be equal to the 1, which means the whole condition now becomes true. If the whole condition now becomes true means then the value which is right hand side of the question mark, that is 0, is going to be driven in y. So we are going to get 0. Okay, this is how the ternary operator works. It is how it is going to check. So if you are going to observe this particular outputs to the corresponding inputs, then we can able to say that it is a NAND operation, right? It is a NAND operation. Okay, so this is how the code works. I hope you guys understood what I have done is okay. So let me execute the code and show you the output, whether it is going to get as we expected or any errors we are going to have. See, we got a waveform. Okay, instead of seeing the waveform, let us see the log file. Okay, see, we got the same output, right? Just verify. Okay, so this is how the ternary operator works. It is also worked in the we can also use this particular ternary operator in the data flow model as well. Okay, Thank you.